Hello, and welcome to this presentation, Getting Started with the CMA180 Tracking Generator. In this presentation, we'll explain how to configure and use the tracking generator functionality of the Rohde & Schwarz CMA180 radio test set. This presentation assumes a basic understanding of tracking generators, as well as a basic familiarity with the spectrum analyzer function of the CMA180. If you're unfamiliar with either of these topics, or if you'd like a brief review, you might want to watch the presentations Understanding Spectrum Analyzers, Tracking Generators, and/or the presentation Getting Started with the CMA180 Spectrum Analyzer before beginning this presentation. The CMA180 Spectrum Analyzer option, K120, enables both Spectrum Analyzer as well as Tracking Generator functionality. The combination of a Spectrum Analyzer and a Tracking Generator can be used to measure frequency response, that is, attenuation as a function of frequency. Note that unlike measurements made using a vector network analyzer, tracking generator-enabled measurements are scalar only. Two categories of measurements can be made using the tracking generator. The first is transmission measurements, which measure the frequency response through a device, such as a cable, filter, etc. The second is reflection measurements, which are primarily used for measuring antennas. Because reflection measurements involve measuring both forward and reverse power simultaneously, an external device called a VSWR bridge is needed when making reflection measurements. There are many ways to use tracking generators, and in this presentation we'll walk through three common scenarios: making cable loss measurements, making measurements of filters, and making voltage standing wave ratio, or VSWR measurements of antennas. Let's start by looking at cable loss measurements. All coaxial cables attenuate radio frequency signals passing through them, and this attenuation is commonly referred to as either cable loss or insertion loss. Cable loss is a function of both the length of the cable as well as the frequency of the signal passing through it. Loss generally increases linearly with increasing length. In other words, doubling the length of the cable also doubles the cable loss. Loss also increases as frequency increases, although this is usually not a purely linear relationship. Knowing the amount of power lost in a cable is very important in many radio frequency applications, so much so that many instruments support entering the external attenuation caused by cables, so that this loss can be taken into consideration when calculating and displaying results. To measure cables using the CMA180's tracking generator, select the Spectrum Analyzer scenario by clicking on the global toolbar, and then choose Spectrum under the Analog tab. Once the application is started, press the folder icon to toggle between Split Mode, which shows the generator and analyzer applications side by side, and the Merged Mode, where only one application is displayed at a time. To configure the tracking generator, click on the Configuration icon in the bottom right corner of the main Spectrum Analyzer screen. Then click the checkbox to enable Tracking Mode under the Tracking Generator tab. The next step is to configure the frequency range over which the tracking generator will sweep, and this is defined under Analyzer Settings. This range can be configured either as a center frequency and span, or as start and stop frequencies. In this example, a center frequency of 2.5 GHz and a span of 1 GHz corresponds to a start frequency of 2 GHz and a stop frequency of 3 GHz. By default, other common spectrum analysis parameters, such as resolution bandwidth and video bandwidth, are configured automatically by the CMA180 based on the defined span, but unchecking the boxes to the left of these values allows them to be manually adjusted. The input connector is specified under the RF Settings tab. This can be set to either RF in or RF COM. The connector used for the tracking generator output is specified under the Generator tab. The tracking generator output level is also configured here. In our example, we'll connect the cable under test between RF in and RF out on the front of the CMA, and we'll set the generator output power to 0 dBm. The tracking generator output is not enabled and disabled separately. Instead, the Start-Stop button in the spectrum analyzer screen controls both the analyzer as well as the generator. Note that a small TM indication appears in the spectrum analyzer screen when tracking mode has been enabled. Results are shown as magnitude versus frequency. The default detector type is auto peak, which sometimes results in a fuzzy trace. Changing the detector type to RMS often produces a cleaner, more easy-to-read trace. Scale settings can be adjusted by zooming in on any areas of interest, or by using the standard click and drag method of zooming. In our example measurement, the cable loss is between approximately 0.4 and 0.9 dB over the range of 2 to 3 GHz. Markers can be used to obtain more precise numerical results, and marker search functions can also be helpful in finding specific values, such as the positive or negative peak. Here, we use a negative peak marker to find the maximum value of cable loss, just over 1 dB at approximately 2.491 GHz. Please see the separate presentation, Getting Started with the CMA180 Spectrum Analyzer, for more information about how to use markers. Now let's look at filter measurements, which are another type of transmission measurement that can be made using a tracking generator. Filters are two-port devices that attenuate signals as a function of frequency. Another way of saying this is that filters pass some frequencies, but block other frequencies. For example, a low-pass filter passes lower frequencies, but heavily attenuates higher frequencies, whereas a bandpass filter attenuates all signals outside of a certain frequency range. Filters are measured by connecting them between RF output and input ports, and a process called normalization can be used to remove the effect of the connecting cables. Basic filter measurements include determining the passband, as well as determining the amount of attenuation both outside and within the passband. Next, let's go through how to make these measurements using the CMA180. As with transmission measurements, the frequency range of interest should be configured under Analyzer Settings. Note that when making measurements of filters that have very high levels of attenuation, about 60 to 70 dB or more, there are two additional settings that may be helpful. The first of these is configuring a higher tracking generator output power, and the second is using a narrower resolution bandwidth or RBW setting. Adjusting both of these settings can help to reduce measurement noise in the stopband regions, and thus allow a more accurate measurement of the attenuation provided by the filter. Calibration can be used to remove the effect of the cables, connectors, etc. in the test setup. The filter or device under test is removed from the test setup and replaced by a simple through to connect the cable ends. Then, under the Tracking Generator tab, Calibrate is used to measure the test setup without the filter. After a few seconds, the CMA180 shows Data Available, and the normalization box can then be checked. At this point, the frequency response graph should look like a straight line at 0 dB. The through is then replaced by the filter, and the filter measurement results can be seen on the screen. Here is an example of a filter measurement made on a bandpass filter. The trace shows relative magnitude, meaning that 0 dB is the no attenuation level. Markers have been placed to determine the center of the filter's passband, as well as its so-called 3 dB bandwidth, that is, the points at which the filter attenuates signals by 3 dB. And in the farther out band rejection regions, roughly 30 MHz or more from the passband center, we can see that out-of-band attenuation is approximately 75 dB. Our final example involves using a tracking generator to make reflection measurements, in this case measuring antenna VSWR. When power is transmitted into an antenna, some of that input or forward power is often reflected back towards the source due to an impedance mismatch between source and load. This combination of forward and reverse power results in the formation of standing waves on the transmission line. The magnitude of the reflection and standing waves is usually highly frequency dependent. Voltage standing wave ratio, or VSWR, is one of the most common ways of quantifying this mismatch, and is calculated from measurements of both the forward and reverse power. A special device called a VSWR bridge is used to separate the forward and reverse power, and allows them to be measured both independently and simultaneously. As with our other tracking generator measurements, the frequency range and other parameters are configured under Analyzer Settings. And as before, once these settings have been configured, Calibrate should be selected under the Tracking Generator tab. Once Data Available appears, normalization can be enabled. The last step is to enable VSWR mode and physically connect the device under test. A VSWR bridge is used to physically connect the CMA180 to the device under test. Recall that the purpose of a VSWR bridge is to enable separate and simultaneous measurement of both forward and reverse power. The CMA-Z547 VSWR bridge, shown here, connects directly to the RF COM and RF out ports on the front of the CMA180, using a pair of Type N male-to-male or barrel connectors. And as mentioned a moment ago, the antenna or device under test is connected to the DUT port. Although we're using the Z547 VSWR bridge in this presentation, other VSWR bridges or types of directional couplers can also be used to separate forward and reverse power when making this type of measurement. There are a few best practices when making VSWR measurements with a CMA180. First, make sure that the RF port configuration is set correctly. That is, which port is input and which is output. When using the CMA Z547 bridge, the generator should be set to RF out and the analyzer to RF COM. It's also important to check that the generator output level and the expected power are approximately the same. The frequency range and power must be set before normalization, and the DUT port of the VSWR bridge should be left unterminated during the normalization process. Let's look at an example VSWR measurement result. Here we see VSWR shown as a function of frequency. The button on the bottom left can be used to scale the axes as needed. Note too that markers can be placed to obtain precise numerical values. Again, please see the presentation Getting Started with the CMA180 Spectrum Analyzer to learn more about markers and automatic marker placement functions. Let's end with a brief summary. The CMA K120 option enables tracking generator measurements on the Rohde & Schwarz CMA180 radio test set. Both transmission and reflection measurements can be made, and these show magnitude as a function of frequency. The frequency range, power, and other settings used for making these measurements are user configurable. There are many applications of tracking generators, and in this presentation we covered 3 of the most common: cable loss measurements, filter measurements, and antenna VSWR measurements. And lastly, please keep in mind that reflection measurements require the use of a VSWR bridge or other type of directional coupler. This concludes our presentation, Getting Started with the CMA180 Tracking Generator. If you'd like to learn more about tracking generators, the CMA180, or other CMA180 measurements, please see the links in the video description.
Thanks for watching. Please subscribe to our YouTube channel and visit us at rohde-schwarz.com.